All right, so today we are going to start the basics of vector addition. Right? So looking at vector quantities, but the first little bit will be a review because it's what you did in Science 10 with collinear vectors. Okay? Collinear vectors would be things like, they both go exactly the same direction, like north and then north again, or if you went north and then south. Okay, so there's only one line along which the object travels. So collinear, they share the line. Okay, and we will also look at perpendicular vectors, right, which would mean you went north and then you turned east, and you went 90 degrees from the direction you were traveling before. All right, so we'll look at those today, as well as the fundamentals of how we draw vectors, represent vectors, and things like that. That'll form the basis for what we start doing next week. Okay, so we talked about just now what collinear vectors are. They're vectors that share a line. Okay, learn that all types of vectors are added by placing them tail to head. All right, what we mean by that is if I had a question that said you went 20 meters north, I would draw that vector like so, 20 meters. Okay, and I would draw an arrow that goes north. Okay, and then you went 40 meters east. Well, where would I draw that?
From the top, 40 meters east.
Exactly. I would draw it from here. I draw it tail to head, like I'm telling a story. First this thing happened, and then this happened. All right? And what did you notice about my lines? They're connected, definitely. Is the 20-meter line shorter than the 40-meter line? Okay, that's one of the conventions of vector diagrams. The length of the arrow represents the magnitude of the vector. You don't have to draw it to scale, like I don't mean you have to pull out a ruler and measure it and be that exacting. That is completely unnecessary, but you need to be mindful of it. Right? I mean, that 40-meter vector is a little more than twice as long as the 20-meter vector, but it gets my point across, and it at least accurately represents what was happening. Okay? Had I made that 40-meter vector instead look like this, then my diagram doesn't really represent what happened. Okay? Because now that 40-meter vector is barely longer than the 20. Right? And so when I finish my vector diagram, which would involve me doing this, that line now doesn't really represent what I did because it should be way over here instead. Does everyone follow me there? So while scale isn't like crucial that it be exact, you have to at least do your best to represent it. Otherwise, when you finish a question, it might not, your answer, your math, might not look like your diagram, and then you'll question it. Okay? And what part do you think you'll question? The diagram or the math? The math. Everybody questions the math. You know what people screw up more often than not? The diagram. Okay? People do the math, right? Because they're more careful with it. Okay? And it's because we all have this idea that, oh man, math is hard and bad at math. Okay, we all have that idea in our head, which is wrong, but that's what we have. Okay? And so we think that drawing pictures is easy and doing math is hard, so we couldn't possibly screw up the picture. When more often than not, it's the picture that's screwed up and it's the math that's right. Okay? But then people go back and try and fix their math. Okay? So just be careful with your diagrams is the message I'm trying to send here. Okay? Do your best to represent those vectors to scale as best you can. All right, that way your diagram and your math are going to say the same thing when you're done. Okay? And it becomes really important when we start having vectors that backtrack on themselves. Okay? Then it becomes really important to have the scale. Okay, obviously we've already talked about this kind of to death because that was back in Science 10 as well. Vector quantities have magnitude and direction. Okay? And that all vector quantities are added the same way. So I had a 20-meter vector and a 40-meter vector. Those were displacement vectors. I could have had a 10 meter per second vector and a 30 meter per second vector. I would still add them the same way. If they were acceleration vectors, I would still draw them tail to head. If they were force vectors, I would draw them tail to head. All vector quantities are added that way. Okay? Because that's the way that they work out. All right, so does that sort of make sense? Before I kind of get into more of it there. All right. All right, so a vector quantity has both magnitude and direction, and the connotation or the convention of drawing vectors is that we use arrows to represent vector quantities. Okay, so arrows are used to represent vector quantities. And the direction of the arrow gives the direction of the vector. All right, which again means you have to be mindful of your scale. It's not usually the length that people mess up in their diagram, it's the angle people mess up in their diagram. Okay, I've had questions where I tell people it's 30 degrees north of east and they draw this line. That might be 30 degrees east of north, but it is not 30 degrees north of east. Okay, that's like 60. Okay, so always be mindful of what your angles look like when you draw them. Again, you don't have to pull out a protractor and measure it exactly, but make sure a 30-degree angle looks like a 30-degree angle and not a 50-degree angle. Okay, just have to be careful of it. All right, questions on that part? Okay. All right, and then the second convention is that the length of the arrow is proportional to the magnitude of the vector. So a 10-meter vector and a 20-meter vector, okay? The 10-meter vector should be half as long as the 20-meter vector. Again, it doesn't have to be measured exactly. As long as you've taken your time to at least represent the scale, you're good. Okay? Because otherwise it takes forever. Because I've had people that are even like more type A than me, and they've got protractors and rulers and they're drawing all their diagrams, and it's really not necessary. All right, questions so far? Okay, let's talk about directions here. So if I have a compass, okay, so north at the top, east, south, and west, right? Where would I draw a vector that is 10 degrees south of west?
There's going to be a 10-degree angle from the west part of it.
So from here?
Yeah.
Okay.
And then go 10 degrees.
10 degrees?
Yeah. I think so.
Something like that. Again, it's not to scale, but it's certainly not 30 or 70. Okay, that would be south of west. So that's how we talk when we're talking with compass directions. We would say south of west. So the way you draw that is, this is your reference direction. Whatever direction is listed second, the angle is measured from that one. All right, so what I did is I put my pen on west, and then I moved in the other direction and got an angle arc. All right, so if somebody tells me I'm going to be going, let's say, 70 degrees north of east, okay, I'm going to put my pen on east. I'm going to go until I think I'm at 70 degrees. There's my line, there's my arc, that's 70 degrees north of east. Okay, everyone kind of follow that? Right, so whatever direction is listed second, that is your reference. Put your pen on that and move in the direction of the other one. All right. So lots of times it's necessary to add one vector quantity to another. Now, can I add meters per second to meters? No. Okay, so when we say that, we mean like two like vector quantities. So two displacement vectors, two velocity vectors, two force vectors, whatever. They have to match. All right. So in this case here, would these vectors be collinear? The two blue ones, would they be collinear? They both point east, right? Okay, so they're collinear. They are on the same line. All right, so if I was told that I had two vectors, one that was 275 meters due east, okay, that's how I would draw it. And we put the magnitude underneath it, right? And then the other one is 125 meters due east. Okay, so what's my total displacement if I follow those two vectors?
400.
400 meters?
Yes. Oh, sorry.
East, yeah, I gotta have the vector on there, right? I mean, the whole point of vector addition is that we are putting vectors on. It's real easy to forget to do that though. Okay, 400 meters east. That would be that line there, okay? We have a name for this line that connects our initial position to our final position, or initial, whatever our initial point and final point are, even if they're forces, okay, or acceleration. We call the line that connects them the resultant. Okay? Because we're going to get to the point where we're going to be adding 3, 4, 5 vector quantities together, okay, and getting a resultant out of them, right? Something like that would look kind of like this. So let's say I had like this first vector, okay, and then I had this vector, and then that vector there, okay? This line here, the red line, would be my resultant. It would be the vector sum of those 3 vectors, right? So while I might have traveled along these 3 paths, in the end, this is what I did, okay, in one step. Everyone kind of follow me there? Right? Now, each one of these vectors that I drew goes horizontally as well as vertically. Okay? Which means they would each have x and y components. Okay? Each one of them. So the green one would also have an x and a y, and the blue one, same thing. Okay? So, with the resultant, it would also have a y and an x. Now, if I take black x, green x, and blue x, and I add them all together, will I get red x? Yes, it will. Okay? If I take all the amounts that I went east, let's say, and add them all together, I'll get my total east, even if one of them backtracks, which is what happens with the y's. Okay? 2 of these go up. One of them goes down. But if I add them all together, making this one negative, will I get red y? I will. Okay? That's where we're headed. We're not there yet. Okay? But that's where we're headed. We draw the vectors tail to head, and then we resolve them into their horizontal and vertical, or x and y components. Then we just add those components together. That's where the trig comes in. I'll only know, so like for this black triangle, I would know what theta is, and I would know what the hypotenuse is. If I know those 2 sides, can I get the other 2? That's where the trig comes in. So you got to do a little bit of sine and cos and a little bit of tan and Pythagorean theorem and all of that kind of stuff that you learned like first unit of Math 10. Okay, you're going to be putting that to use here. Okay, questions so far? All right, so when I use the term resultant, that means I'm looking at what all of these add up to over the course of the whole question. Okay, now how would this look different if instead of this 125 meters being east, it was west? Yeah, I'd subtract it, or I'd add a negative, whichever, mathematically they're the same. Okay, we just say add sometimes because we always say it's vector addition. We never say it's vector subtraction. Okay, so most of the time we add a negative. But to change this, obviously the diagram wouldn't look like that anymore. Now the diagram would look like this. Okay, so the 275 goes east, the 125 goes west, and now my resultant is only that long. Okay, so if I went 275 minus 125, I would get 150 meters east. I still end up east of where I started, right? I do travel west. I do have it at my westerly part, but I end up east of where I started. Okay? Everybody all right with that idea? Okay, that's the basics of vector addition. That question.
Is the resultant just the displacement?
In this case, it's displacement. If I had 2 velocity vectors, it would be the average velocity. If it was acceleration vectors, it would be the average acceleration, or net acceleration. For force, which is in the second unit, we use this with force, it becomes our net force. So imagine if I have like a ball on the ground, and two people are pushing it. Okay, if one person pushes to my left and I push forward, which way does the ball go? Right, it would go, so I'm pushing forward and they're pushing to the left. This is the way the ball's gonna go, right? See, it works no matter whether it's force or velocity or acceleration. Putting two vectors together, tail to head, always tells you what's gonna happen, okay, as a result, hence resultant, okay, for our final thing. Okay. All right. Now, what if it's perpendicular? Okay, is it going to change a little bit of what I do? A little bit. Now it's going to bring Pythagorean theorem and trig into play. Okay? I don't have to do that if it's all in a straight line. It's just plus and minus. Right? So now this object goes 275 meters east, and then it goes 125 meters north. Okay, so how do I figure out my resultant now?
A squared plus B squared equals C squared.
Right, use the Greek geek. Okay, Pythagoras is the Greek geek, by the way. Okay, spent his whole life studying triangles. So, we are going to do a squared plus b squared equals c squared. So, to get my resultant, okay, which in this case is going to be my total displacement, okay, I'm going to say my total displacement will be the square root of 125 squared plus 275 squared. Okay, so that'll get me the magnitude of my resultant. But my resultant is a vector quantity. So I also need a what? Okay, how am I going to get that direction? Don't?
Would it be maybe like a degree north of east?
It absolutely would be a degree, a certain angle north of east.
So you have to find that.
I have to find that.
So you could just find like,
Yeah, I mean, I'll have all three sides of the triangle by then, right? So I could use any trig function I want at that point to find that angle. All right, so first thing we're going to do is get the magnitude. So we'll go 125 squared plus 275 squared. All right, so it's 302.07 meters long. I'm not going to do my significant digits yet. Okay, 302.07 meters in length. Now, I need to find its direction. Okay. Since I know all three sides, I could use sine, cos, or tan. For me, I would use tan because it's going to use the two sides I was given and not the side I calculated, just in case I mess up. Okay. If I messed up with my Pythagorean theorem, I don't want to use a number that's wrong. Okay. Then at least I get part marks for getting the angle right. Okay. So that would be my logic. But at this point, you could totally use any trig function you want because you have all three sides. Okay, so looking at theta, okay, so I'm going to use tan. So the tan of theta equals the opposite side divided by the adjacent side. Okay, so this is the adjacent side because it's touching the angle, and this is the opposite side. All right, so my 275 is the adjacent, my 125 is the opposite. So I want the angle, so I'm going to bring tan over here, and that'll mean tan to the minus 1, or inverse tan, of 125 over 275 will get me that angle. All right, so I'm getting 24.4. If you did not get 24.4 when you punch that into your calculator is still in radian mode. Okay, when we're doing this, your calculator must be in degree mode. If you are taking math right now, that means you're going to have to remember to switch it back and forth pretty much every day because you use radians in math a lot and you never use it in physics. Okay, we always want you in degree mode in physics. Okay, so 24.4, okay, we have three significant digits for this question. So if it was asking me what was the total displacement, I would say the total displacement is 302 meters at 24.4 degrees north of east. Okay? Would there be more than one correct answer for this? There would be. 302 would have to be part of that, but what's the other thing?
Couldn't it be the other side of it, and then it'd be east of north?
Exactly. I could have the complementary angle, and that would also be correct, as long as I had that it was east of north. Okay? And that would also be acceptable. And that happens as we get into more complex vector diagrams. Everybody draws them a little bit differently. Some people would draw your resultant and draw the triangle this way. So if this was my resultant, okay, some people would draw the triangle this way and they would get north of east. Okay? And some people would draw the triangle this way and get east of north. But either way is fine. We're still talking about the same line.
What angle would you have to find to get east of north? Would it be,
It would just be 90 minus 24.4,
oh,
right? So we'd be looking at 65.6, I think.
right.
Yeah. Okay. Yeah. Or you would have your triangle would be flipped, right? This would be the 275, and this would be the 125. So your 125 is now the adjacent side, and your 275 is now the opposite side. All right. How are we feeling about the trig part of this? Okay. This is kind of the start of it. On Monday, you're going to see resolving a vector into its components and then adding the components together, which is what I showed you with that messy 3-vector diagram. Okay, so that's what we just did. That's the math of it there. Okay, and we're going to look at a couple examples here. Okay, so this one's collinear. Okay, so let's just have you guys write this one down. This is a race in the most boring town in the entire world. Yep. So if we're going to add these ones together, I mean, obviously we don't need to draw a vector diagram for this because all the vectors are forward and that's pretty simplistic. But if we were going to do that, okay, we would want to be careful about our scale. Okay, we got 10 meters, we got 5 meters, and we got 25 meters. So I would say our first 5 or 10 meter vector, whoop, come on. Okay, so that would be my diagram. I don't know if that 25 is quite long enough, but I mean, I get the idea across. It certainly isn't misrepresenting what happened in that race. Okay, everybody with me there? So my total displacement then would be 40 meters forwards. Done. Okay, that's all there is to it. The collinear ones are pretty easy. Okay. Here's one that's going to make you think. I would like you guys to try number 7. Okay, there's a little bit of an algebra trick here. Okay, a diagram is helpful, right? But there's a little bit of a trick with that one.
Do you have to do trigonometry?
There is no trigonometry. They're collinear. Okay, but there's a bit of an algebra trick, so think about it a little. Okay, so type.
I don't have the answer.
Okay, we're just going to go through it. We'll walk through it. So what happens with this one is we have this car that drives 500 north kilometers. North kilometers north. Okay. Okay. So 500 kilometers. And then it drives 3 sequential displacements south, each of which is 50 kilometers longer than the previous displacement. The final position of the car is 50 kilometers north. So that means its total displacement after this whole trip is this little red line here, which is 50 kilometers. Okay, so each of the 3 segments adds up to, or sorry, all 3 segments add up to 450 kilometers south. Okay, so I can say then that 450 is equal to the sum of those 3 parts. Agreed? Okay. So I know the second one is 50 kilometers longer than the first. I know the third one is 100 kilometers longer than the first. Is that fair? All right. What's my problem then? I don't know how long the first one is. So I'm just going to say that it's x. And then I'm going to say that the second vector is x plus what? 50. And then I'm going to say the third one is x plus 100. Okay, so I'm going to move the 50 and the 100 over here. Everyone okay with that? Okay, so I'm going to bring that over by subtracting, and I'll have then that 300 equals x plus x plus x. Well, what's x plus x plus x? 3x. 3x. How long is the first track? 100 kilometers. It's an algebra trick. Okay? It's not really about vectors, except that the vector diagram kind of helps you figure out what they add up to, which is the first step. Knowing what those three segments add up to is what you need in order to figure out what the first segment is. So your first segment is 100, then 150, and then 200, which adds up to 450. Okay? Everybody all right with that? Now, with the bouncy ball here. So if you drop a bouncy ball from a height of 10 meters, so we're going to start up here, ball's going to fall 10 meters. Okay? Then it's going to rebound 8 meters. Okay? And then it's got to fall back down. And then it's going to go to 4 meters. And fall back down. Okay? And then it's going to go to 2 meters. Okay. It doesn't mention anything about it falling back down after that. It says that that's where the question stops. All right? So what's my total displacement? 8 meters
So,
down. Yeah. Okay. Now, what's my total distance? 10 plus 16 is 26, plus 8 more is 32, plus 2 more is 34, I think. Okay, we got to go up and down. The part that people forget on this one is the back up parts, okay, or the back down part. Like they forget that when they draw the diagram. Okay. Now, did I draw these tail to head? Well, I did. I just didn't want them all overlapping, right? If I'd have drawn this diagram like that, it would have been pretty hard to see by the end. Okay, so I just spaced them over, but they're still tail to head because it was all collinear. Okay, so this is the last one I want to work on today. I think we got time. Oh yeah, we got lots of time. Okay. Important thing for this one is the vector diagram. So draw the vectors tail to head. There are 3 of them. Okay? 3 vectors, and they're not collinear. Well, 2 of them are, but they're not all collinear. Okay, so draw this one out and see if you can figure out what the total displacement is in this question. Okay, so in walking around I can see that most people have the diagram drawn correctly and they have the magnitude of the result. What do we also need? We need the direction because it's a vector quantity. Okay, so you guys did a good job with this. She went 0.8 kilometers south. So she started here. Okay, she went 0.8 kilometers south, and then she turned and went 1.2 kilometers east. And then she went 0.3 kilometers north. Okay, so that means then that our resultant, okay, her total displacement, is this blue line here. All right, and I saw that on like basically everybody's sheet. Okay, so that's good. Now, that's going to help me because I need to know the magnitude and direction of this. Now, could you have drawn that triangle this way too? Either way, it doesn't make any difference which way you draw that triangle. All right, except for the trig you're going to do. So I need to find out what the total displacement is. In order to do that, I need the 2 sides of this triangle, or what we would call its horizontal and vertical components. Okay, so how big is the horizontal component? 1.2 meters. That's how far east she went. right? So I know that this side is 1.2 kilometers. And this side here, she went 0.8 south and came back 0.3 north. So how big is this side? 0.5 kilometers. Headed south. Okay? All right, now that I know those two sides, now I can do Pythagorean theorem to get this side. So when I go 1.2 squared plus 0.5 squared, it comes out to 1.3 kilometers, I believe. Yes?
Yeah.
Okay. Next thing I got to do is I've got to get my vector. I can't just write the displacement is 1.3 kilometers. Displacement's a vector quantity, so it needs to have a direction. So the way I drew the triangle, I'm going to use tan because it's my favorite trig function, because I'm that much of a nerd that I have a favorite trig function. That's okay. That's who I am. Okay, tan to the minus 1 of the opposite side, 0.5, divided by the adjacent side, 1.2. If you drew the triangle the other way, that's fine. You just have these flipped. Okay, so when I do that, so second tan of 0.5 divided by 1.2, I am looking at 23 degrees. What's my direction? The way I drew it, south of east. If you drew it the other way, you'll get east of south. All right, because I went from east, I went south of east. Okay, so south of east. If you have 67 degrees east of south, that's fine. Okay, everybody all right with that one? Okay, so that's a pretty typical perpendicular vector question. Right? But it leads us to what we're going to talk about next week, which is finding the components of our vectors and of our result, the horizontal and the vertical components. So that's what I was telling you about here earlier. If I had these two vectors, okay, where would my resultant go?
The outside of 10, like 6.
Yeah. Okay. It always goes from the beginning to the end. Yeah. Okay. So that green line would represent my total displacement. That would be my vector. That would be y, and that would be x. Okay. So if I'm going to get my total displacement, I need to know green x and green y. As we said before, green x is going to be blue x plus red x, knowing that red x is negative. All right? And green y would be blue y plus red y. Okay? Red y, yeah. I can add the y's together, I can add the x's together. All right? So how would I find x? I know the hypotenuse of this triangle, and I know this angle. X is my adjacent side, yes?
You use the cos ratio?
Yeah, I'd use cos. Okay? I know that cos of 40 degrees equals x over 10, adjacent over hypotenuse. I'm okay with that. So if I want to find x, I just multiply both sides by 10. 10 times the cos of 40 would give me x. Okay? How would I get y? I can use sine. Okay? Y would equal, okay, so sine of 40 degrees equals y over 10, opposite over hypotenuse. Okay? And I would just multiply both sides by 10, and I would have y. Okay? That's the trig part. Probably doesn't seem as bad as I made it out to be, does it? Okay? I mean, this, I know, because my kid is taking this right now in Math 10. This is like the first thing you do in Math 10. Okay? Is you learn how to do the sides of a triangle if you have a trig function and you have a side and an angle. And that's all you're ever going to have to do. Okay? In fact, the stuff you do in Math 10 is quite a bit more involved than what I'm going to ask you to do with what you learn. Right? So there you go. You can have the weekend now and go, oh, I'm not as afraid anymore. Or Yeah, hopefully. Okay, all right, so, reminders here. I will not be here on Monday. Okay, Mr. Van Erp will be here, and he's gonna play the lesson with me showing you how to do a question just like this. Okay, and then you guys can kind of get started on that. I'm sure you'll do just fine, and then we'll go over some more on Tuesday. On Tuesday we're gonna do our labs, right? Okay, and then Wednesday we'll go over some more of this stuff. Okay. I will try and get those labs marked today if I can. Okay, but you will definitely have your marks by Monday. Obviously, I won't be able to go over the lab with you on Monday because I won't be here, but you'll have your marks. I will go over it on Tuesday morning before we start the next thing. Okay?